That all have extended on the involved.
Yeah. So she actually works at E, so do you want me to mark it?
Yeah, yeah, so how are we gonna do that? Just in pencil, Carol, and put the date of Wednesday.
Do you want to think right now? You do right now.
Yeah, yeah, maybe here and Carol,
Okay.
yeah. Okay. Let's finish up chromatography, you guys. Happy Friday. Come to me. Focus on me. All right. So let's do some recap questions and continue with the lecture and finish up chromatography today, I hope. Can you name examples of absorption chromatography? Yeah.
TLC.
TLC, everybody loves TLC. You guys are, yeah, TLC can be partition chromatography. It can work at absorptive, but what I meant under absorption chromatography, what modes of separation can also be counted as absorption chromatography? Lisa, your hand was up. Were you gonna say?
Yeah.
Okay.
We love it.
So let's solid chromatography, so you can use like silica gel as your solid and then like a mixture as your.
Okay, so what do you call the mode of separation when you use silica and let's say ethanol or hexane? What do you call this mode of separation? You have silica as a phase and a non-polar solvent as well. What do you call it? Reverse phase, normal? So that would be normal, but that's not absorption. Okay. Under absorption chromatography, you guys remember what could be counted as absorption, absorbed to the stationary phase via particular molecular interaction. Thank you, Carolyn. Affinity chromatography can be considered absorption chromatography, ion exchange chromatography, hydrophobic interaction chromatography. So any mode of separation that involves molecular interactions with a solid stationary phase, that is going to be considered absorption chromatography. All right, what molecular interactions between solute and stationary phase are involved in size exclusion? Please, no.
So for the size exclusion, there's no.
There is none. So size exclusion, you don't have interaction with the stationary phase. Actually, those solutes are just separating based on their size. In ion exchange, what are the, okay, that's it.
It's electrostatic.
Electrostatic, so ionic interactions, electrostatic interactions where you have positive and negative charges interacting with each other. In hydrophobic interaction chromatography, that's it. Hydrophobic interactions, yes. In affinity chromatography, yeah.
It can be any one.
It can be any form of molecular interactions. It can be a combination of hydrophobic, electrostatic, van der Waals, interactions, hydrogen bonding. So anything non-covalent, but a very specific interactions between a compound and a ligand on the stationary. All right, so what's the difference between cation and ion exchange? So when I say cation exchange chromatography, what am I separating? positively charged molecules, and your stationary phase will have functional groups that are negatively charged. Very good, and the opposite is true for anion exchange. All right, how do we increase the strength of the mobile phase in reverse phase chromatography? Let's have the reverse phase chromatography. All of you did caffeine, half of you did caffeine. Yeah, but we did talk a lot about reverse phase. You have a non-polar stationary phase and a polar mobile phase. How do we increase the strength of the mobile phase over time?
Increase the concentration of the polar and solid in the mobile.
So it's increased the concentration, but not of the polar, because in reverse phase, you have non-polar stationary phase, and you start with a very polar mobile phase. You start with water or a high percentage of water. Over time, you increase the concentration of the organic solvent, so that you make your compounds that are interacting with the non-polar stationary phase like the mobile phase better and lead with the mobile. All right, how do we increase the strength of the mobile phase in hydrophobic interactions? What's your mobile phase, if you remember, with hydrophobic interaction from the process? When do you start with a mobile phase that is a salt solution? Okay, so over time, what do you do with that salt solution? Increase, decrease, huh?
Increase the concentration.
Decrease, you said, or increase? In this particular chromatography, it's decrease the concentration of salt. Because if you remember, and if you don't remember, that's fine, you can study this for the upcoming quiz on October 17th. What? Is it 17th?
Yeah.
All right, in a week. A week and few days. All right, so in hydrophobic interaction chromatography, your protein, you're salting them out. That means you start with a high salt concentration so that they precipitate on the column. In order for them to come out, you decrease the salt concentration. Sometimes you just change it from salt to water, from salt solution to water, and then the protein comes out. In ion exchange chromatography, how do we increase strength of the mobile?
But how do I want to increase both the pH and the salt concentration?
You change the pH and increase the salt concentration. The pH, sometimes you increase it, sometimes you decrease it. So it can go either way. But yes, so it's a change in pH and an increase in salt concentration. In affinity chromatography, how do I increase the strength of the mobile phase? Affinities are very specific interactions. So, does anybody remember or want to guess? Stan?
I remember it's adding, I don't know what you call it, but you're like,
Ligand.
you add ligand so that it interact with the binding site, and it makes it so that the substance doesn't bind into the stationary phase.
Okay, so you're like 80% right. So on the stationary phase, you have a specific ligand, we call it. Sometimes it is an antibody to a specific antigen, sometimes it's an enzyme inhibitor to a specific enzyme. So in the mobile phase, you can add, if it's an antibody antigen interaction, you can add antibodies similar to what you have on the stationary phase. Then your antigen will interact with what's in the mobile phase and leave the column. Sometimes if you have lectins as ligand, you add lectins to the mobile phase. Sometimes you don't do that. You change the pH and change the ionic strength. So you change those very specific interactions you have with the affinity between this compound and the stationary phase. You change the pH, you change the ionic state, you change the charge on the molecule, you will change its structure, it won't bind anymore to the column. So that we call non-specific dilution. And when you add a legend specific, we call that a specific solution. So all of that was covered last week. One thing I would add, how you would increase the strength of the mobile phase in normal phase chromatography. And that's what Sarah said at the beginning, increase the water concentration in normal phase. Okay. What is the order of elution in hydrophobic interaction control? The least hydrophobic will come out first or come out last in hydrophobic interaction. The interactions are hydrophobic. So do you expect the least hydrophobic to elute first or the most hydrophobic to elute? Or leave the column first? The least hydrophobic will leave the column first because it will have the least interaction with your stationary phase. All right, so in ion exchange, the least charged or the most charged, the particular charge, whether it's positive or negative, the one that has the highest valence electrons or valence ion, or the one that has the least. The least. Very good. So the less interaction, again, the faster the elution. In silent exclusion chromatography, is it the smallest that elute first or the largest that elute first?
The largest.
The largest, because it doesn't go through the pores, it's gonna go with your void pore. Very good. So these are the things that you want to review after you study. Make sure you understand all of this. Now I'm going to move on to a very important topic. Why isn't that moving? There. Okay, so here in chromatography, whether it's GC or HPLC, I'm going to talk a little bit about GC. You want things to separate. Okay, I mean, define chromatography as separation. We want things to separate so that we can identify them, first detect, then identify, and perhaps quantitate. So I wanted to separate these compounds within a solution or a mixture of gases and GC. You want it to be as separated as possible so that I can identify or detect these separate compounds, identify what they are, and then quantitate. Sometimes you really don't need very good separation. You just want to identify, you don't want to quantitate. If you don't want to quantitate, it doesn't matter if they're co-eluting as long as you can identify this first peak and the next. But if you really want to do quantitation, it's the best way to get them separated so that you can get this individual area under the curve. So we want to learn how we develop separation. It's very important in chromatography. If you don't develop separation or reach to the acceptable separation that you want, then it's chromatography fails, basically. So the first thing you do before this, before knowing any of this, you want to do caffeine analysis. Before you start thinking about caffeines and alkaloid, does it like hydrophobic or non-polar interaction? Before you start thinking about any of this, and you are given a task of separation using chromatography, what would be the first thing you do? The very first logical thing that any researcher would do. First, yeah.
I would just look at caffeine or what,
You look at
just look at the molecule or like what characteristics of your, what you're trying to
before that.
before.
Very first thing that we do as a graduate student, as a researcher, as a scientist. You can look up what's been done previously. Thank you. Just somebody out there in the globe has looked at caffeine before you're doing it. whatever. So somebody out there must have developed a method. So you look at what is published, what is known, oftentimes you can find something out there as a start. You do it, it's not gonna work 100%. You have a different system, different column, it's not gonna work, but it gave you a basis to start thinking. Then you're gonna do what Kevin is talking about, like, I don't understand my model, I don't understand what it is, what am I separating, is it polar, is it non-polar? How many components I have? Am I trying, it's a mixture of 10 phytochemicals, or is it just honey and I have glucose and fructose, there's hardly any sucrose? So what am I looking at? How many components I need to worry about in my sample? And do I care about complete separation, or it's okay to be overlapping a little bit? What's the resolution for the separation that I want to see? And is it a qualitative or quantitative? Is it qualitative where I want to see present or not? Or what's the identity of these polyphenols, let's say? Or I want to identify and quantify. So all of these are factors that I need to think about when I want to develop my method of separation using chromatography. Okay, so then I understand my compound, I know what I want, I have my objective. Then I want to say, okay, what's the mode of separation I want to follow? Are these compounds charged compounds? Do I want to use cation or anion exchange? Or are these compounds partially polar or relatively non-polar? I want to use reverse phase or normal phase. So I start thinking about the mode of separation. Okay, so first of all, since we are covering liquid chromatography, I already said I'm doing liquid chromatography. The type of chromatography is liquid, but sometimes you have to think, do I want to do HPLC or do I want to do GC? And then what's the mode of separation? Once I solve this part, then I go, okay, in reverse phase, there is many different options for stationary phase. I have a C8 column, C18, C30, for example. What do I want? I want a very non-polar stationary phase. I will go with C30 for my carotenoids, for example. I want relatively non-polar, like caffeine. Okay, I'll go with C18. So I pick my stationary phase and then the mobile phase. Do I use water and acetonitrile? Do I use water and methanol? So it depends. Sometimes methanol is chosen over acetonitrile. If peaks are very close with each other, it's a less polar, relatively polar organic phase. So acetonitrile is much more hydrophobic than methanol. So you have that question actually in one of your lab reports. When do you use methanol and why? So sometimes if I have peaks that are very close to each other and I'm using acetonitrile as a very strong organic solvent, if I use a more polar organic solvent than methanol, I can separate them a little better. I will enhance the selectivity of my column, of my selectivity of the interaction of the stationary phase and the mobile and the constituents, I'm sorry. Okay, so basically there's a lot of things I have to think about, and then it doesn't end there. Once I established the mode of separation and the stationary phase and the mobile phase, then I have to think about different elution properties. Do I want to use isocratic? What does isocratic stand for? Just remember, let's see if you remember. Isocratic mobile phase meaning?
Medora, keeping the constant ratio of mobile and the same throughout.
Yes, keeping the same characteristic of your mobile phase, constant mobile phase throughout. So, and then gradient, you are achieving the concentration over time. So do I go with isocratic? Sometimes things are easy, price exclusion, isocratic. You don't change over time. Sometimes, if you're doing carbohydrate analysis using refractive index, you change the concentration and your refractive index will change, will impact how the different compounds are selected. So there is no choice there, you have to go isocratic. Sometimes you start with isocratic and see if my run is so long and I get that much separation, and this comes out at 30 minutes and this second peak comes out at 60 minutes. Oh dear, that's just a lot of time in between and I'm sitting doing nothing. I increase the strength of the mobile phase so this peak will come out sooner and I still get separation. Flow rate, temperature, these are very important. When we talk about flow rate, you need to get the flow rate that works the best, shortest analysis time without co-evolution. We don't want them to come out fast and come out together. And also you don't want your run to be 3 hours long. So you increase the flow rate, which is the number of the milliliters of mobile phase per minute. So sometimes it's 0.5 mils, sometimes it is 1 ml per minute, sometimes 1.2 mils per minute. So basically you adjust that as well. And the temperature. The temperature, those of you that did HPLC, you see that we put our cloves in a small oven where we control the temperature. And the temperature usually we control it anywhere between room temperature, 25 degrees C, to probably 40, 45 degrees C. The higher the temperature, the faster is the mobility, the shorter is your analysis time. So we try to figure out again where we have good separation, no overlap, shortest analysis time. And also temperature that is controlled will also prevent having what we call fluctuation due to room temperature changes. Because if the room temperature changes, your retention time will change as well. And that will mess up things for you. So you want to control that temperature. Okay, so there's so many choices out there, and sometimes the same set of compounds can be analyzed in so many different ways. So water soluble, they can be non-ionic, for example, or ionic. If they're non-ionic, you can do reverse phase chromatography. You start with water and then increase the strength of the mobile phase. If they are ionic, you can do ion pair and still do reverse phase. The ion pair means you add an ion to block the charge in the molecule, then they can interact with your nonpolar stationary phase. You can do ion exchange if they are ionic. So there's so many options. Now you would go, okay, if I have 3 references and every reference is telling me I can do 3 different ways. I can do either normal phase, ion pair, or ion exchange for the same compound. What do I do? If I have 3 papers and each are using a different step, what do you do in this case? How do you choose? What factors you take into consideration to choose between 3 different methods that will all work?
Which one's the greenest? The green chemistry?
Well, I know that. Which one's the greenest? Sustainability, save the earth. Good. What other consideration you would take?
What's more accessible?
Thank you. What do I have in my lab? Sometimes you want to be green, but your supervisor is stingy, doesn't have money, and tell you this is what we have, this is what you're going to use. So whatever is accessible for you. That's usually the logical thing to do. Okay. But if you have 2 or 3 and you have the luxury, you choose sustainability, go for it. Yeah. All right, now I want to introduce few terms that will help us in understanding resolution a little better as I go through the next thing. So, retention time. We all know that retention time means the time it took on the column before it came out and it was detected. Sometimes you hear retention volume. We don't do much with volume. Oftentimes you deal with retention time. Retention volume is the volume of the mobile phase that was needed for the compound to leave the column. So either retention volume or retention time. Oftentimes you'll hear retention time, and this is the first thing to identify your compound with. If you have a standard and it comes out at a particular time, if it's a simple chromatogram, that's the first thing that you will use to ID your compounds, retention. Sometimes you don't have a standard, you only have a reference, something that is published. And let's say caffeine in this paper has a retention time of 14 minutes. In this other paper, it has a retention time of 15 minutes or 16 minutes. What impacts the retention time is also the void volume of your column. So how big is your column? What are the dimensions? What is the volume it takes to go through to the detector, your solvent front? So this time here to the solvent front is different from one unit to the other. You have different column dimension and also sometimes different lengths of tubings and everything. So to eliminate this difference that might come due to the setup of your instrument, we calculate a factor, separation factor called alpha. So we get the adjusted retention time. So we get the retention time of your first peak and subtract the solvent front, and you get the retention time of the second peak and subtract the solvent front. You get the adjusted retention time of second peak over the first peak, and that's the factor of separation. That's constant. Okay, that is constant under similar conditions. The same column, the same mobile phase, the same dilution. This is all will make it constant. Okay. So resolution, you can actually calculate resolution. So it is designated in a simple way and also in a little more complex to give you three factors that impact resolution. First of all, the equation of resolution here is 2 delta T. Delta T is the difference between retention time for peak 2 and retention time for peak 1. So that's delta T. And W2 is the width of the first peak, the second peak, and the width of the first peak together. So it's an inverse relationship to the width. That's something I wanted to remember. The wider your peak, the poorer is your resolution. The sharper your chromatographic peak, the better your resolution is going to be. So you always want those sharp, nice peaks. Okay. Now that we understand that, I want to talk about the three important factors that impact resolution. Column efficiency, column selectivity, and column capacity. So there are three different factors that will impact the resolution. So the efficiency is designated by theoretical plate number. The N is for theoretical plate number. I'm not going to talk about that in a minute. And then the alpha is your factor that we just talked about. The alpha is the the adjusted retention time of 2 over the adjusted retention time of peak 3. So that's the peak 1, sorry. That's the selectivity, okay? How selective your saturation phase is to your particular compound. And then capacity of your column. How many functional groups I have, and how many compounds I'm able to interact with my column. Capacity factor. Okay, so we're going to talk about efficiency, then the selectivity, and then the capacity. Let's talk about efficiency first. That has to do with the theoretical plate number. All right. I have here, take 2 columns, okay? Well, let's say we're starting with a brand new column. Brand new, you just bought it. You start with a specific theoretical plate numbers. This is a plate, this is a plate, this is a plate, this is a plate. This one has, let's say, 4 plates for compound X, for a specific compound. Over time, the more you use your column, you're going to lose efficiency. And then instead of having 4, you're going to have 2. Okay, what does that mean? Let me demonstrate. And we say theoretical because the column is not really divided into any plates. The column is a column that has a stationary phase inside of it. That's why we say theoretical. So this is your column. And it has a set number of plates, theoretical plates, at the beginning, brand new column. So, but in reality, what's happening is when you put your sample, your components in the sample are going to reach equilibrium. And every time they reach equilibrium, it is a theoretical plate. And that's how they move down the column and elute. So this is your mobile phase. So you have your compounds separating, and then they go into your stationary phase and move out with the mobile phase, in and out, in and out, in and out, until they leave. Every time they reach equilibrium, that is a theoretical thing. And every time they get an equilibrium, this is 1 equilibrium, 2 equilibrium, 3, 4, 5, 6. The more they reach equilibrium, the faster they reach equilibrium, the narrower is your peak. So the bands, as they go in, they start separating. And as they diffuse, if they stay tight bands and they don't spread out, you get a really nice sharp peak. Over time, you're going to lose efficiency. And then it's going to take a very long time for the compound to reach equilibrium. So instead of 6 theoretical plates, I end up with 4, and instead of a very sharp column peak, I get diffusion, and my bands are now the diffusion. They diffuse at a bigger height than I want them to. Instead of staying sharp, diffusing sharply, going out, in and out in a sharp band, they start to diffuse, and then I get wide peak. And then if there is supposedly another peak here for another compound, I'm going to see this. I'll get cold dilution. I lost efficiency in my column. My bands are no longer moving tightly and equilibrating efficiently. They are taking longer time to equilibrate. The bands are spreading within the column. My compound is spreading over wider distance. Then when they leave, it takes a long time. This is time, okay? This is, let's say, absorption or refractive index or the FID index, whatever it is. So you're measuring here absorption over time. That means it is taking really long time and it moves through the column more than it moves in and out into the mobile phase. Is that concept okay? Do you want me to repeat anything? Yes, Karen.
Is there, so I have two like questions, I guess. Is there any way to clean or your column or make it more efficient after it's kind of deteriorated?
Yes, yes and no. If you take good care of your column, there's something we call conditioning the column or regenerating the column. You can wash off impurities, you can replenish the functional groups, but at some point you can't do very much. The functional group might have lost completely through your multiple runs, and sometimes if you don't take good care of your column, you run it at, let's say, 100% acetonitrile over an extended period of time, and then you don't do equilibration or anything, then you cannot regenerate. That's your first question.
Yes, the second one is how do you determine your theoretical number?
Yes, how do I determine the theoretical number? That's a very good question. It is here. The N equal retention time over the sigma, which is equivalent to, this is the width, and this is your retention time, and you can actually calculate that. So the way you do it is, let's say I get a caffeine standard, and then I have my very first time using this fresh column right out of the box. I run caffeine and I determine my number of theoretical plates. And then after 6 months, I'm using the same column, I determine the N and it goes down. Then I know that with the same compound, every compound will have a different theoretical plate because every compound equilibrates differently on the column. That good, Kevin? Good questions. I like that. Any other question? Anything else I need to repeat? Okay, very good. Now, the number of theoretical plates is really dependent on the length of the column. Is that how long is your column? If I want to eliminate the length of the column, because this can be variable, depending on the column I have at hand, I can correct for that. I can calculate something called height equivalent of a theoretical plate. The HETP is height equivalent of a theoretical plate. So here, I'm determining only the height here. Height equivalent of a theoretical plate. So I'm just determining this height. Okay, so this is the one that is going to change over time, is going to increase over time when I lose efficiency. Okay, if this height equivalent theoretical plate is increasing over time, I'm losing efficiency. So, and I think Gary might have mentioned, I think he did mention the height equivalent theoretical plate from a GC perspective. Okay, so the height equivalent theoretical plate is impacted, so the length of the equilibrium or the height equivalent theoretical plate is dependent on 3 factors. A, B, C in that equation. U is the flow rate. This is mass transfer. This is longitudinal diffusion. Diffusion. And this one is eddy diffusion. So eddy's diffusion, longitudinal diffusion, and mass transfer. So what is longitudinal diffusion? Let's say you have a river, and in the river there are pebbles. And then let's say you have large rocks. If you have a flow, you have really large rock here versus very small pebbles, and you have the river is flowing, or your mobile phase is flowing. So the river is flowing. If you hit the large rock, it's you're gonna go in multiple directions. The water, the mobile phase, whatever it is gonna go in multiple directions around that large particle or rock, or whatever you call it. If you have really small, well-packed particles of your stationary phase, you really don't have that much of a change in direction. You don't have your particles going in different ways. Here, if that happens, you take a long time to reach equilibrium, height equivalent of theoretical plate, whereas here, your height equivalent of theoretical plate is narrower. So here you have a shorter one, and here you have a larger one. So if eddy's diffusion is large, so you have diffusion in multiple directions around, and then so your compound is taking different pathways within the column, and that's delaying its equilibrium. The band is going to broaden, and you would have a very wide peak. So one thing to deal with that is to get a column that has stationary phase with small molecular weight, very well packed, then you can have a very small area. So now, what is longitudinal diffusion? Longitudinal diffusion is when you start on a column, your sample starts here at the beginning of the column. It's going to move down. So you're going to start seeing going from a highly concentrated to a less concentrated. So it's diffusing longitudinally down your column. And then it's going to go out and in. But it's also going down. So you don't want so much of diffusing within the column. You want it to go in and out, in and out. If you have large pore size, your particles, so if you take one of these particles and enlarge it, so I'm taking one of these particles, it has large pore size, your compound is going to go through and be delayed, and then this will broaden as you go, and then you end up with really wide peak. So basically, the higher the B value, the higher is the height. So you want very small particle size with very small pores. All particles are porous. So you don't want to have really big pores. But also what's impacting this factor is the flow rate. If you have a very slow flow rate, like 0.2 ml per minute or 0.1 ml per minute, very, very slow, So your mobile phase is going very, very slowly. Then you have more of the compound going down through the column longitudinally rather than in and out of with your mobile phase. So if you have a very slow mobile phase, you can have a wide peak. So the flow rate is important. Now, the mass transfer, that has to do with going between the stationary phase and the mobile phase. This factor is also impacted by the flow rate. So if you have really very, very high flow rate, you don't have time to equilibrate. So the compounds are moving very, very fast, they're not equilibrating, and you don't have good separation. So you will get two peaks very early on and not separated from each other in like the first 2 minutes. So you have poor resolution and you have more diffusion within the column. So the flow rate plays a dual factor here. Inverse relationship and direct relationship. So that's why flow rate is not always in one direction. You don't want to always increase flow rate without the ceiling. So you need to always have this optimal flow rate, not too fast, you don't get equilibrium, and not too slow, if you will get longitudinal diffusion. So that's why the U here is present in different factors. So you want to find your conditions. You want to find your optimum flow rate where you have the lowest or the shortest height equivalent of theoretical flow. The shortest it is, the sharper the peaks, the better is the resolution. So that's the effect of the flow rate, and the temperature plays a really important role in the mass transfer and the movement. Movement and reaching equilibrium faster. So you increase the temperature a little bit, you have lower viscosity of your mobile phase, you have more kinetic energy, you have more movement, you reach equilibrium faster, and then you have better resolution and narrower high equivalent of theoretical. Okay. All right, I didn't finish lecture, but I stopped where I stopped last year. Isn't that cool? Okay, so Monday and Wednesday, you'll have Gary with mass spec. And then on Friday, I'll be finishing up this lecture and covering HPLC. I don't know if I'll be able to come here physically. I might be not physically well. If I'm able, I'll be here. If not, it'll be me on camera, but you guys here. Okay. Yes, let me stop recording.